As I look here on page 19, I'm going to start off with this number 11, where we have this object right here. This object is pulled upward at a constant speed, so we know that there's going to be balance in these forces. Constant speed showing us that there's going to be balance, no acceleration. So I indicate the system, putting these dash marks around the object. Gravitational force, mg down, tension force up. I put in the equality marks to indicate that these forces are balanced. And then we can get the sum of the forces in the x direction. There's nothing there, so then we add them all up, and the x direction equals to 0. We get the sum of the forces in the y direction, tension force up, minus mg down, tension force up, minus mg down. This all equals to ma in the y direction, giving us 0 newtons. We can look at an object falling without air resistance. That's going to be free fall, to where the object is in the gravitational field. So we have just mg down. Sum of the forces in the x, that's left and right. There's nothing there, equals to 0. So the sum of the forces in the y, we have this negative mg equal to ma. We could actually solve for what this a is. In this case, the acceleration would be that acceleration due to gravity. It is less than 0. It's a negative 9.81 meters per second every second. As I look up to one of the more complicated ones, let's take a look here at number 9. So when I took number 9, what I did here is I changed the axis. So I made it so that way the axis on this is now having what we would look at a normal x and y going left and right, and then y is up and down. And I drew the forces on this object where the mg is pointed down towards the center of the earth, but the normal force going parallel to that surface, and this tension force getting pulled up and to the left. Now on our new scale, I have the tension forces only in the x direction, the normal force is only in the y direction, and I have indicated my x and y coordinate plane to be like so. So that way my mg, which is pointed towards the center of the earth, now is going to give me some mg in the y and some mg in the x. So we're going to have some x component and a y component of the gravitational force. And that's due to the axis that I chose. So now I have the normal force in the y and mg in the y. I set them to be equal to one another because this object is motionless. There's balance in this force in the y direction. We also have mg in the x. That's going to be equal and opposite to that tension force. And that mg in the x is going to be equal to that, so it's balanced. Now if we were to cut this cord right here, and let's say this was a frictionless plane, that we cut that cord, there's no more tension force. It's this mg in the x that causes it to accelerate, to make it go down the ramp. And that's why we see this force here acting in this x direction. So we can then get to the sum of these forces, where this mg in the x minus that tension force that does exist equals to ma in the x, which is equal to 0 newtons. The sum of the forces in the y direction, that's this normal force up minus this mgy down, normal force up minus mgy down, equals to ma in the y. We can do similar looking at number 10. When we look at number 10, I shifted the coordinate axes, so that way the x and y coordinate plane would lie along the plane that the object is on. So I have this mg down towards the center of the earth, but giving us an mg in the y and an mg in the x yet again. I'm calling this second surface that the surface is on, I'm calling that surface number 2. So we're going to have a normal force number 2 going up in the y direction. I also have surface number 1, that's this surface, and there's going to be a normal force with respect to that surface now in that x direction. So we can draw our free body diagram based on the axis that we chose, giving us a normal force 1 in the x, mgx here in the negative. So sum of the forces in the x, normal force 1 minus mgx, is going to give us ma in the x, which equals to 0 newtons. It is motionless. It's not, the motion is not changing. Then we can get to the sum of the forces in the y, so that second normal force up minus mg in the y down, that's all equal to 0 because it's once again motionless. It's not accelerating in the y direction, nor is it nor is it accelerating in the x direction. As I continue down to number 15 and 16, we have a ball that's in a parabolic curve you're going to see that we should get the same type of motion. While the ball's thrown in the air, there's no air resistance, so only mg down, only mg down. The forces that are only acting on this object while this ball is in the air, no matter its point in its path, it's only gravitational force, only the gravitational force, causing it to have an acceleration at all times as this negative g, this negative 9.81 meters per second every second.